Three cosmic visitors, a tailless interstellar comet, a golden-tailed classic, and a mysterious newcomer, have converged in the dawn sky, defying every rule astronomers trust. This is the story behind Breaking, where rare alignments and shocking silences in the data raise questions scientists never expected to face. How could objects streaking toward the sun show almost no tail when every textbook says they must? In the next few minutes, you will see why what happens between November 6th and November 16th could rewrite our understanding of the solar system, and why the true stakes are only just emerging. In the pre-dawn hours of early November, the eastern sky offers a rare spectacle. Three comets draw close together, crowding the constellations Virgo and Leo. 3I Atlas, C 2025 V1 Borisov, and C 2025 K1 Atlas. For a few days, from November 6 to 8, their apparent positions tighten to within a patch of sky no wider than a human fist held at arm's length. Each comet claims its own territory in this gathering. Interstellar 3. I Atlas hovers on the Virgo side, its path traced by precise calculations, but its appearance faint and enigmatic. C 2025 V1. Borisov sits near the border between Virgo and Leo, harder to spot, its glow subtle and easily lost in the morning haze. Then there is C 2025 K1 Atlas, the unmistakable anchor. Against the backdrop of Leo, K1 Atlas flares with a golden tail, bright, structured, and classic in form. It behaves like a textbook comet and provides a clear visual and scientific point of comparison. Sky charts for these dates show the trio forming a loose triangle, with K1 Atlas's tail pointing away from the sun and stretching across the stars of Leo. The geometry is fleeting geometry. By mid-November, the comets begin to drift apart, and the window for this tight grouping closes. For observers, timing is everything. The best views come just before sunrise, when the sky is still dark enough to reveal the comet's faint glows but the horizon is clear. Each object sits about 15 to 20 degrees above the eastern skyline, low enough that even a few clouds or city lights can spoil the show. For backyard telescopes and well-aimed binoculars, the trio appears clustered just above the horizon as the first hints of dawn color the sky. The alignment is more than a curiosity. It allows astronomers to compare three very different bodies under nearly identical observing conditions. The bright, textbook tail of K1 Atlas, providing a direct, side-by-side contrast to the more enigmatic profiles of 3I Atlas and Borisov. The tight timing, just days when all three are visible together, adds urgency to every observation. For both professionals and amateurs, this is a chance to catch rare behavior in real time, to log not just positions and magnitudes, but differences in form and activity that might otherwise go unnoticed. As the morning sky shifts and the comets move on, the data gathered during this brief window will become the foundation for deeper analysis. The geometry of early November, with its unique clustering and the golden tail of K1 Atlas as a visual anchor, sets the stage for the questions that follow. Questions about what these objects are made of, how they behave, and what they reveal about the solar system and beyond. Disagreements began to surface almost immediately as the first images of C 2025 V1 Borisov were posted to minor planet forums and amateur astronomy networks. Of the roughly 10 earliest observational reports, 8 described a nearly perfect round coma, no tail, no hint of elongation, even under careful scrutiny. These accounts came from a mix of small backyard telescopes and mid-sized professional instruments, each logging details about exposure times, filters, and sky conditions. The consensus seemed clear. Borisov was a tailless comet, its appearance more like a fuzzy star than the sweeping forms usually associated with these objects. But two reports stood apart. Both claimed a faint, narrow tail extending 50 to 72 arcseconds from the nucleus, barely above the noise threshold. In one case, the observer had stacked dozens of long exposures using a sensitive CCD camera and applied aggressive digital filtering to enhance faint features. The other relied on a slightly larger instrument and a different reduction pipeline, but the result was similar: a marginal, almost ghostly extension trailing away from the Sun. Both flagged their findings as tentative, noting the low signal-to-noise ratio and the risk of artifacts from imperfect flat fielding or cosmic ray hits. These conflicting reports sparked debate, not just about Borisov's physical nature, but about the reliability of the methods used to study it. Astrometric measurements, pinpointing the comet's position against background stars, proved straightforward. But photometric analysis, especially for subtle features like a faint tail, was far more subjective. Some teams used standard broadband filters, others narrowband gas or dust filters. Calibration routines varied, as did the criteria for separating real cometary structure from detector noise or background gradients. Even the choice of reference stars and the way images were stacked could sway the results, sometimes producing a tail where none existed, or erasing one that was barely there. The tension between amateur and professional observers grew as new data rolled in. Amateurs, often first on the scene, were quick to share raw images and reduction logs, eager for feedback and peer review. Professionals, bound by institutional protocols and publication schedules, moved more cautiously, sometimes withholding preliminary findings until they could be cross-checked and formally submitted. The gap in methodology became a source of friction. Some amateurs accused professionals of overcautious skepticism, while professionals pointed to the dangers of overinterpreting low-confidence signals. In the background, the need for a standardized approach became obvious. Without consistent reduction pipelines and clear criteria for what counted as a detection, the ambiguity around Borisov's tail or lack thereof would persist. Each new report added another data point, but also another layer of uncertainty. The only agreement was on the numbers: 2 faint tail sightings, 8 showing only a coma. The story of Borisov's early days became as much about the process of science as about the comet itself. Every image and log entry fueling the ongoing debate over what exactly was being seen. Solar activity surged in late October, just as the 3 comets tightened their triangle in the morning sky. On October 21, a G3 geomagnetic storm swept across Earth, sparking auroras at unusually low latitudes and flooding astronomy forums with speculation. Some wondered whether the solar wind might trigger outbursts in the comets, or even sculpt their tails in real time. But as the debate grew louder, the evidence remained stubbornly one-sided. No clear change in activity, no sudden brightening, and most strikingly, no new tail on either 3I Atlas or Borisov. Space weather modelers stepped in, pointing out that while the timing was dramatic, the comets were far from Earth's magnetic reach, and the solar wind's effects at their distances were weak and diffuse. The alignment of solar storms and comet clustering was, by all available data, a coincidence. A reminder that correlation does not mean causation, no matter how tempting the narrative. The question of data sharing took on new urgency as the world's eyes turned to the comets. In late October, the Chinese National Space Administration, CNSA, released a single much-anticipated image from its Tianwen 1 Mars orbiter. The frame, snapped as 3I Atlas swept past Mars' orbit, offered a rare view from deep space. Yet the image itself, a faint, pixelated smudge, left researchers hungry for more. Scientists across Europe and the United States voiced frustration. The file's low resolution and lack of supporting data limited its scientific value, and requests for raw telemetry or additional frames went unanswered. Some in the community saw this as a missed opportunity. One planetary scientist wrote in an open letter that new spacefaring powers must balance mission pride with international obligations to science. Others defended CNSA's caution, citing technical limits and the desire to avoid premature conclusions from noisy data. The Tianwen 1 episode exposed a growing divide in how cometary data are handled on the world stage. NASA, the European Space Agency, and most major ground-based observatories have long traditions of rapid, open releases, sometimes posting raw images and spectra within hours. By contrast, CNSA's guarded approach fueled a new round of private negotiations and public appeals for transparency. Behind the scenes, teams jockeyed for time on the Hubble Space Telescope, the James Webb Space Telescope, and the Mars Reconnaissance Orbiter's high-rise camera, hoping to secure the first high-resolution look at an interstellar visitor from beyond Earth's orbit. Proposal emails describe the November window as a highest-stakes competition, with every observing hour counted as precious. Through all this, the need for rigorous, reproducible datasets became impossible to ignore. The G3 storm's spectacular light show and the Tianwen 1 image's global attention both highlighted the same lesson. Science demands more than coincidence and spectacle. Only careful, transparent data, shared and scrutinized across borders, can turn fleeting cosmic alignments into lasting discoveries. As November wore on, the world waited for sharper images and harder numbers, aware that the real story of these comets would be written not by rumor or rivalry, but by the evidence still to come. Hard numbers. Spectroscopic data from the James Webb Space Telescope has delivered the first hard numbers on the nature of 3I Atlas. Infrared spectra reveal a coma dominated by carbon dioxide, with a carbon dioxide to water mixing ratio measured at 7.6, far higher than typical solar system comets, and a clear outlier even among interstellar visitors. Water vapor is present, but at much lower abundance, hinting at either deep burial beneath a processed surface or a nucleus where water ice is simply scarce. The dust detected in the coma is faint and exceptionally red, more akin to the weathered surfaces of distant centaurs than to the bright, reflective grains seen in active comets. Dynamical evidence. On the dynamical side, astrometric tracking through perihelion and beyond shows almost no sign of non-gravitational acceleration. Where most active comets experience subtle but measurable shifts in their orbits, nudged by jets of outgassing material, 3I Atlas remains remarkably stable. Orbit-fit residuals from multiple teams agree. The object's path is governed almost entirely by gravity, with any possible deviations falling below current detection thresholds. This stability, paired with the high carbon dioxide content and weak dust activity, narrows the field of possible physical models. Working model. The evidence now points to a small carbon dioxide-rich body with a surface that limits water-driven outgassing and suppresses classic tail formation. The red dust and minimal acceleration suggest a compact, possibly sintered crust, perhaps altered by cosmic rays during its long journey between stars. For dynamicists and spectroscopists alike, these findings constrain the possible origins and current state of 3I Atlas, moving the discussion from speculation to a framework grounded in measurement. A new framework now guides the search as the world's telescopes track 3I Atlas and its tailless companion C 2025 V1 Borisov. The leading explanation among comet scientists centers on the concept of a refractory mantle, a hardened, dust-rich crust that insulates the nucleus and suppresses classic cometary outgassing. Laboratory studies and thermal models suggest repeated solar heating can sinter the upper layers of cometary material, forming a shell just millimeters or centimeters thick. This layer acts as a barrier, trapping most volatiles beneath the surface and allowing only small sunward jets of carbon dioxide to escape through cracks or vents. The result is a faint red coma with little dust and no sweeping tail, even during close solar approach. This model fits the evidence from 3I Atlas, where high carbon dioxide to water ratios and minimal non-gravitational acceleration point to a crust that is both chemically unusual and physically robust. Not all voices are satisfied with this conservative view. Some online forums and informal discussions have floated more speculative ideas. One thread proposes that Borisov could be a fragment split off from 3I Atlas, perhaps during a distant encounter in another star system. Others see cosmic meaning in the trio's sky alignment, suggesting a deeper orchestrated significance. These theories remain unproven, lacking any dynamical or compositional evidence, but they highlight the sense of wonder and the need for healthy skepticism when confronting the unknown. With Borisov's perihelion approaching on November 16th, the next phase is clear. Observers are urged to watch for any sign of tail formation, sudden brightening, or changes in coma structure. The checklist is simple. Monitor brightness and morphology nightly, compare amateur and professional datasets, and scrutinize every faint extension for signs of real activity. As new images and spectra arrive from ground and space-based observatories, each finding will be weighed against the mantle hypothesis and the more imaginative alternatives. The coming days will test both the models and the observers, as every dataset adds another piece to the puzzle. Right now, astronomers worldwide sift real-time data, searching for answers these tailless objects refuse to give. If 3I Atlas and Borisov defy comet physics, our models of planetary formation and interstellar chemistry are at stake. The sky is not just a backdrop, it is a test of what we think we know. Tonight, uncertainty is the only thing that shines brighter than the comets themselves.